Good morning, ladies and gentlemen. Thank you for joining today's webinar. I'm Roy Liu from Moldex3D EMEA team. Today's webinar's topic is reducing warpage and shrinkage with simulations. When it comes to warpage and shrinkage, we have to consider what is the main cause of warpage and shrinkage. So let's introduce first what is warpage. The warpage is caused by the differential distortion, just like a sample here. You can see this plate that has a warpage, and you will warp downward. And because the uneven stress will lead to the shrinkage, so this part will start to warp downward. And there are three main causes that will cause the warpage. The one is temperature difference, and the other is packing effect, and the last one is fiber orientation. So firstly, I will introduce the temperature difference effect. As you can see, this is a sample here, and at the topper of the part, we have 3 cooling channels. On the contrary, there are 4 cooling channels at the bottom of the mold base. So at the upper size, we'll call it the hotter size, and the bottom size will be cooler than the upper. So in the upper size, because here has a heat accumulation phenomenon, so it will have a large volumic shrinkage. On the other side, which is bottom size, it will have a small volumic shrinkage. So we can see that as the mold open, this part will start to warp toward the harder size, because in the harder size we have a large volumic shrinkage. As for the packing effect, the packing pressure or packing time is a crucial reason that will lead to the warpage. So in this case, in this region, it is near the gate. So this is a region where have a high convective pressure. On the contrary, in this region where it is far from the gate, so the packing pressure is not able to transmit the packing pressure efficiently. So when we demold in the region near the gate, we will have a low shrinkage. As for the region far from the gate, we will have high shrinkage. So we can see the figure here. It is the packing pressure result. We can see in the near the gate region, we have a high packing pressures. As for here, it will have the low packing pressures. So the warpage result will show that in this area, it will have a small volumic shrinkage. As for here, it has a large volumic shrinkage. The next one is the fiber orientation effect. And when it comes to fiber orientation, we have to consider the flow direction, because when the metal is injected into the cavity, the fiber will keep its direction along the flow directions. So if the fiber has a directions that is same as a flow direction, and we will say it will have a low shrink rate, because it has enough stress to resist the volumic shrinkage. As for the vertical direction, which is in these directions, it will high shrink rate, because it doesn't have fiber orientation to resist the shrinkage phenomenon. So in order to improve the warpage, there are four main parameters that will affect warpage. The one is geometry, mobile, and also processing and material. So first of all, the geometry, we can consider to change part dimension or change thickness. As for the mold design, we can consider the number of runner or the gate location to have to that the part have access to the perfect packing effect. And also we can consider cooling channels, which means if we have more cooling channels, we can decrease the heat accumulations and the warpage will be improved. Then the processing. We are able to change the male temperature or mold temperature. And also we can enlarge the packing time or increase the packing pressures to improve the warpage. The final is the material. We can consider the PVT material property, which is related to the volume shrinkage phenomenon, and also the crystallinity and fiber or filler orientation. So we, by consider these four main parameters, we are able to improve the warpage. So in this part, we have provide four real cases to validate these parameter changes. So the first case is from Pegantron, which is win the first prize of Global Innovation Talent Award in 2018, and then use the change in the material to improve warpage. This is a back cover of laptop, and in the middle of this laptop, it is aluminum part insert, and all the products has a length of 270 millimeters, and width is 160 millimeter, and the thickness is ranging from 0.5 to 1 millimeters. The material for the part is PC, and the part is aluminum. Okay, this is a layout of the hot runners and cold runners, also the cooling channels. So the original design, they felt that the value of warpage is equal to approximate 8 millimeters. And because of a part insert is in the middle of this part, so in the middle of this region, it is strong enough to resist the volumic shrinkage. So the warpage tendency will shows like this. It will warp downward. Each of this product will have a large warpage result. In order to improve this case, so they set their goal to decrease the warpage less than 1 millimeters. Before figuring out the methods to improve the warpage, they see how these are main reasons to affect the warpage. So we can see the temperature affect warpage and shrinkage affect the warpage, which is 1.4 millimeters, and the other is 6.7 millimeters, which means the shrinkage effect is a main cause that will affect warpage in this case. So they consider to implement materials with different percentage of glass fibers to enhance the fiber orientation effect. Okay, so they choose two new materials with glass fiber, which is D151 plus 10% of glass fiber, and the other is D452 plus 40% of glass fibers. After having a simulation analysis, we found that using the material with 10% of fibers, it will have a large value of warpage, which is approximately 3.2 millimeters. As for the 40% of glass fibers, it will improve the warpage to the 0.6 millimeter. In other words, they use a higher percentage of glass fiber, and it can decrease the warpage phenomenon. So this is comparisons between the original material and the new materials. So we can see here the X direction warpage with the 40% glass fibers has the most improvement, which is only have a 0.6 millimeters warpage. Okay, in the next case study, it is from Dura Automotive Systems, and it is also winning the special prize in our Global Innovation Talent Award in 2018. They choose to change the part designs to decrease the warpage. This is briefly geometry design introduction, and this part is a side window encapsulation. It has a length at approximately 400 millimeters. The width is equals to 330 millimeters. As for the thickness, it's ranging from 0.5 millimeters to 13.5 millimeters. The material they use is PVC. You can see here, this is a thickness variation. The region here, it have a very thick regions at 13.4 millimeter. As for the other places, it is very thin compared to this region. Okay. Actually, this is a assembly product. In the previous page, it is a PVC encapsulation, but in order to have a simulation analysis, they have to use assembling. This is this is PVC encapsulation, and it is transparent glass, and this aluminum insert, and the other one is glass round channel, which is GRC. And it is a real product, looks like this. If we have cross sections at this region, we can see the purple color is the PVC encapsulations, and the yellow part is a GRC, which is glass round, which is GRC. So in the first simulation result, we can see the temperature at end of cooling. In these thick regions, it will have a high temperature, which is heat accumulation here at almost 200 Celsius degrees. So with these heat accumulations, the warpage, it will have a high warpage, about 7 millimeters. And this GRC will move toward the x-axis, and the region here will start to twist along the GRC as a as an axis. So in order to improve the warpage, they figure out to core out these thick regions, and instead they use ABS inserts to put inside here, and the PVC product here will have a thinner region, and the heat accumulation could be decreased. So this is the changing design of the insert here, which is material is ABS, and the cross section here will show that here it is ABS insert here. So we can compare the original design and modified design, and we can see that the temperature at end of cooling, it will have a great improvement from 200 Celsius degrees to 153 Celsius degrees. As for the molten core at the end of cooling, in the original design, in this part, in this region, it will still have some male PVC here, but in a modified design, we can see at the end of cooling, it will almost have solidificated. So with this ABS insert, we can see this a great improvement to from seeing the value of molten core. As for the warpage result, the original design has a warpage of approximately 7 millimeters, but after they modified the design, the warpage had to decrease to almost 2 millimeters. And it is the twisting tendency of this product. And you can see the modified design, it has a slightly twisting along the GRC. So by using the ABS insert to core out the encapsulations, it helps to decrease the heat accumulations and improve the warpage. Next, it is a case study from linear AMS, and they won the special prize in 2015 of Global Innovation Talent Award. They used to change the cooling channel design to improve the warpage. And this is a rifle stock arm brace. It has a length of 180 millimeters, and the thickness is from 2.5 millimeters to almost 30 millimeters. The material is TPE. Before changing the cooling channel, it is a multi-site difference and temperature distribution. It is clear that this region has a high value of mold temperature, and in the core of this product, it will have a high temperature, which has a high heat accumulations. So in order to improve this phenomenon, they change a cooling design, which is use a conformal cooling design. And the difference between these two designs is that like this part, they use these cooling channels to insert this core, and also in this part. So it will help to remove the heat and decrease the heat accumulations. You can see the result of the simulation result. The modified design has a 95 Celsius degrees at these core regions compared to the original designs at more than 150 Celsius degrees. And we can also see the mold temperature difference has a great improvement. In these regions, it will have the low mold temperature. Okay. So after modify the cooling design, which is using the conformal cooling design, they improve the warpage largely, and they improve the 17% of warpage. So by changing the cooling channel design, it will truly help to improve the warpage. In the final case study, it is a cell phone cover, and they change the gate designs to improve the warpage. So you can see this product here. It's a cell phone back cover. Interestingly, in the middle of this part, it has a thin region, which is about 0.5 millimeters compared to other places, which is 1 millimeters. And the material is using PC. Okay, this is the layout of the cove runner, and with the 3 cashew gate. In the mail from time, we can see here. It will probably have a welded line, and doesn't have a balanced flow, because in this 3 gate, the pressures will transmit from here, but in the middle of this part, it will hardly have access to the pressure, either the filling pressure or packing pressure. So we can see the packing pressures at end of packing. Almost the packing pressure will implemented at the edge of this part. However, in the middle of this part didn't have access to the packing pressures. So in the middle of this part will shrink more than the edge of this part, and will have a Z displacement of 1.5 millimeters. In order to improve the warpage, they choose to change the gate design into a single gate, and the gate location is also changed to near the thin region. By this design, we can see the mail front here and the packing pressures. Compared to the original design, in this thin region, it truly have more packing pressures. So in this by this design, we can see this have a large difference between the original design and modified designs. And in a modified design, we have improved the warpage to 0.6 millimeters. So changing the gate location or the gate number, it will have a improvement of warpage. In the last part, I will introduce the 3D VSCM, which is 3D volumic shrinkage compensation method. And it is a concept of flow chart of the compensation method. In the figure A, it is a target design. after we simulate this part, we have a simulated target design, which will have a warpage phenomenon, and the part will shrinkage along the x, y, and z axis with distance. And by utilizing the compensation method, it can compensate the distance to the part. So we can use this deform model to rerun the simulations. So the final simulation compensating target design will match the target design. So this is the 3D volumetric shrinkage compensation method. In this case, it will have a shrinkage and bending effect by using the compensation method, and we reverse the deformations, and we can have a final model to match the target design. So how to use this compensation method? So this is a workflow of compensation method in R70 Studio. And this function, you have to click the deformation and can see this icon here, which is export deform model. After selecting this icon, you can see the interface here. But importantly, there are two kinds of options you can choose. The one is deform model, and the other is deform model after compensation. The deform model is according to the dimensional between original and calculated model. Our product will automatically compensate this distance along the x, y, and z axis to have a deformed model. As for a deformed model after compensation, we can compensate the percentage that is we input, and with this input compensation percentage, our program will export the deformed model with the compensation percentage that we select. And it is a demo video that will show you how to use this function. Before using this method, we can use a measure this distance to determine how much we have to compensate. So this is x, y, and z axis distance. And after we click the deformation, we have to change the option to an isotropic to change the x, y, and z percentage of compensation, just like the field here. After we change the compensation, we click the export deformation model, and we have to choose the scale factor to the -1, because the warpage result of these scale factors, the +1 is to show the warpage result. On the contrary, if you choose the -1, it will have a deformed models. So this is a briefly demo video of shrink compensation method. Okay, next is today's webinar's conclusions. because of uneven stress, the differential distortion that will cause the warpage, and by changing the three main factor which will consider these three main factors: the temperature effect, packing effect, and the fiber orientation. It will help to improve the warpage. Also, we can implement four parameters that will affect warpage. We can change the part design or mode design. Even we can change the processing by enlarge the packing time or packing pressures, or even we can change the material. Just for example, to use the material mixed with fibers. And the last one is by using the 3D volumic shrinkage compensation method. It will help us to have a model that will approach into the real dimensions.